Hello again, and welcome to part 3 of calculus, a new approach using simple school algebra. In part 1 of this presentation, we discussed the elementary algebraic introduction to tangents and differential calculus that has its roots in ideas of René Descartes. In part 2, we then discussed all the standard rules of differentiation within the class of rational functions. As is well known, algebraic functions, such as polynomials and rational functions, only cover a small part of functions. In particular, many of the most interesting applications, for example, the growth of populations, compound interest, radioactive decay, waves, motion of planets, and more, cannot be handled by such elementary functions. Instead, other functions must be used. The simplest and perhaps most important ones, such as exponential and trigonometric functions, are known as elementary transcendental functions. We shall now focus on exponential functions. E sub b at x equals b to the power x, where b is a positive number. As experienced mathematicians know, these functions are the eigenvectors of the differentiation operator d. That is, they satisfy that d applied to e sub b is equal to some constant lambda sub b multiplied with a function e sub b. This property is of fundamental importance in the study of operators in many different contexts. Therefore, to study the process of finding tangents, that is, the process of differentiation in the context of exponential functions, should really reveal all the most important concepts. Let me give a quick introduction to exponential functions, beginning with compound interest, a familiar concept in finance. Suppose you invest Q sub $0 in a certificate of deposit that pays an annual interest rate of 6%, compounded annually. This means that after 1 year, your investment will have grown to Q sub 1 equals Q sub 0 plus 0.06 times Q sub 0. And that is equal to Q sub 0 times $1.06. At the end of the next year, that amount Q1 will have grown to Q2 equals Q1 times 1.06. And that is the same as Q sub 0 times 1.06 squared. Continuing this process, at the end of the nth year, the initial investment will have grown to Q sub n equals Q sub 0 times 1.06 to the power n. So we have introduced the exponential function e sub 1.06 with the base b equals 1.06, defined by e sub 1.06 at the value n equals 1.06 to the n for positive integers n. For an arbitrary base b, we have the analogous exponential function e sub b defined by e sub b at n equals b to the power n equals b times b and so on times b, altogether n factors, where n is a positive integer. The simple counting argument gives the familiar formula that b to the power n plus m is the same as b to the power n multiplied with b to the power m. While this formula looks almost trivial, it is really fundamental for determining the proper values of exponential functions for inputs different than natural numbers. This relationship, e sub b at n plus m equals e sub b at n multiplied with e sub b at m, is known as a functional equation of the exponential function. The early example from finance suggests that it is useful to consider exponential functions for non-integer values. For example, the bank may want to use monthly compounding. So one needs to know the values of 1.06 to the power 1 over 12, or for several such compounding periods, 1.06 to the power n over 1/12 for any positive number n. As already mentioned, the functional equation determines how to define E sub b for more general numbers so that the functional equation continues to be valid. For example, the functional equation requires us to define E sub b at 0 as follows. Since E sub b at n is equal to E sub b at n plus 0, which by the functional equation should be E sub b at n multiplied with E sub b at 0, and E sub b at n is different from 0, we divide the above equation by E sub n, and it turns out that E sub b at 0 must equal 1. Next, since the functional equation E sub b at minus n multiplied with E sub b at n, if the functional equation remains valid, this must be equal to E sub b at minus n plus n, which equals, of course, E sub b at 0, which we just determined must be equal to 1. So one must define E sub b at minus n as the reciprocal of E sub b n. We note that this justifies a familiar way of writing 1 over a as a to the power minus 1. More generally, this justifies the analogous familiar formula 1 divided by a to the power m is equal to a to the power minus m. More intriguing is that the functional equation requires that E sub b at the value 1 over n raised to the power n. So that means you get by the functional equation E sub b at 1 over n plus 1 over n and so on. Altogether, the summand 1 over n occurs n times. So adding it all together, you get E sub b at 1, which of course is equal to b. So E sub b at 1 over n must be the nth root of b. In particular, if you choose n equals 2, this implies that the base b must be a positive number, since it is the square of some number. For example, if you take the square root of 2, and we know it's not a rational number, so it is clear that the extension of the exponential function to rational numbers requires us to enlarge the set of rational numbers to include such non-rational roots. We shall not go into these details here, but we will simply assume that the exponential function E sub b with b positive is defined for all rational numbers r, and that E sub b of fr is positive, and that the functional equation remains correct for all rational numbers r and s. Furthermore, one verifies that the exponential functions also satisfy the equation E sub b at the value r times s is the same as E sub b at the value r raised to the power s. And this is most easily checked when r and s are positive integers. Now, let us look at tangents to the graphs of exponential functions. To keep matters simple, let us consider the case where the base is 2. That is, we look at E sub 2x, which is equal to 2 to the power x. Its graph is readily visualized with a graphing calculator. It looks really quite simple, just like a line that is gently bent according to some rule. Surely it looks like there's a tangent at every point, which touches a graph in a double point. If you pick a point here, well, you draw the line that's tangent, and it is a double point, because if you rotate the line just a little bit, it will cut the graph in two different points. Concretely, let us now look at the point 0, 2 to the 0, which is a point 0, 1, and consider lines through that point given in point slope form by y equals 1 plus m times x, where m is usually the slope. Its points of intersection with a graph of e sub 2 are the solutions of the equation 2 to the x is equal to 2 to the 0 plus mx, which we can rearrange as 2 to the x minus 2 to the 0 minus m times x minus 0 is equal to 0. Now, guided by the algebraic case that we considered in part 1, we look for a factorization of 2 to the x minus 2 to the 0 equals q at x times x minus 0. The slope m equals q at 0 would turn the solution at x equals 0 into a zero of multiplicity greater than 1. The problem is that in contrast to polynomials, we do not know any explicit formula for the factor q. Yes, as long as x is different from 0, we surely must have q at x is equal to 2 to the x minus 1 divided by x. But this quotient is meaningless for x different from 0, for x equal to 0, excuse me. And there's no known simple way, say by canceling or other means, that could tell us what q at 0 looks like. So we must find another way to capture this critical value, q at 0. Surprisingly, the algebraic approach, especially the critical factorization, easily suggests such an alternative approach. Consider a polynomial p and its standard factorization, p at x minus p at a is equal to q at x times x minus a, where q is also a polynomial. It is easy to see by standard estimations that any polynomial is bounded over any finite interval. In particular, there exists a constant k positive, so that q at x, the absolute value of that, is less than or equal to k for all x with absolute value of x minus a less than or equal to 1. The factorization then implies the estimate absolute value of p of x minus p of a is less than or equal to k times absolute value of x minus a for all x at distance less than or equal to 1 from a. And clearly this estimate shows that as x gets closer to a, then p of x gets closer to p at a as well. After all, if this expression here gets smaller and smaller, multiplying by k, it will still get smaller and smaller, just at a different speed. And that forces that this expression here also gets smaller and smaller as x approaches a. So in symbols, we write p at x approaches p at a as x approaches a. And this property is very, very fundamental for functions. We have discovered that polynomials enjoy this fundamental property that is known as continuity of the function at each point a. Now, in case you are familiar with this notion of continuity and you're hooked on the formal proof that involves things like epsilon and delta, just choose, based on the above estimate, the quantity delta is epsilon over k, and you're done. But there's no need to make things so complicated and abstract looking. The estimate speaks for itself, and it confirms what we can readily see by graphing polynomials with the graphing calculators. Now, we want to emphasize that no formal definition of limits is required yet. In fact, it is the above estimate that suggests the idea of limit in the simple case where the value of the limit is known and equals the value of the function. So we may introduce a notation, limit as x approaches a of p of x equals p of a. This is just a way of summarizing what we have discussed a moment ago. Note that this approach is really the reverse of the standard one, which begins with limits typically, and then introduces continuity as a special case of limits, proves various limit theorems, and ultimately then applying these various theorems concludes that polynomials are continuous everywhere. I wonder which approach works better for our students. Returning to the critical factorization, let us apply what we just learned to the factor q, which is also a polynomial. So we conclude that q is also continuous at the point x equals a. Therefore, p of x minus p of a over x minus a, which is equal to q of x as long as x is different from a, q of x, this expression, approaches q of a, which is a derivative of the polynomial at the point a, as x goes to a. We see that the derivative, which was obtained by a precise, simple algebraic process, can also be captured by an approximation process via quotients that are defined for x different from a. In fact, what we discovered is, in essence, the classical idea of Newton and Leibniz, who captured derivatives by concepts that eventually led to the formulation via limits that has become the standard way to introduce students to derivatives. But rather than starting off with a novel and deep idea of limit, our approach handles algebraic functions by an elementary process that only involves central concepts of algebra, school algebra. And the approximation process then appears as a simple consequence of the key algebraic factorization, combined with the most basic estimation. Incidentally, what we just discussed for polynomials works just as well for rational functions. It just takes a bit of additional work to show that every rational function R is locally bounded. That is, given a point A in the domain of R, there is an interval I sub A that goes from A minus delta to A plus delta, where delta is some positive number, maybe very small, so that R is bounded on this interval. It then follows, as in the polynomial case, that R is continuous at A. Therefore, we obtain a most simple proof that every rational function is continuous at every point in its domain. Let us now return to the exponential function, where we are dealing with a quotient q at x is equal to 2 to the power x minus 1 divided by x for x different from 0. Motivated by what we just discovered in the algebraic case, we may try to capture the critical value q at 0 by approximating it by q at x as x goes to 0. Of course, this presents a new challenge, namely how to investigate such an approximation process. In particular, as we do not know any value for q at 0, there is no way to attempt any estimation as in the algebraic setting. We can gain some insight into the problem by considering numerical approximation with the help of a calculator. For example, let us look at q evaluated at 10 to the minus k for k equals 1, 2, 3, and so on. So these are numbers 10 to the minus k that gets closer and closer to 0. So with xk equals 10 to the minus k, we obtain the following values for q at xk. Here is a table. Here are the various inputs, and this is what the calculator gives us, just the first 10 digits. And you notice that these values seem to approximate something that certainly begins with 0.693147. That's what we have here. These numbers here stay constant all the way, and there's just changes here at the next digits. Well, could you have guessed this? No way. And the question, of course, is, do the numbers q at 10 to the minus k really approximate something? That is, do they have a limit as k gets larger? And if indeed there is a limit, what type of number is it? Well, we surely do not have answers to these questions. On the other hand, we recognize that if we want to solve these problems, we are really confronted with a new difficult problem whose solution will require some new ideas and new concepts. So the moment has come that we need to introduce a precise concept of limit. Furthermore, in order to ensure that limits, such as the one we discovered as being critical for an understanding of the exponential function, do indeed exist, we must enlarge the number system appropriately. We already have been prepared for this, for example, by recognizing that the rational numbers are not sufficient for capturing numbers such as square root of 2, or most values of exponential functions, even if one only considers rational inputs. A thorough examination of these difficulties led mathematicians in the 19th century to introduce the axiom of completeness that must be satisfied by the enlarged number system. The numbers so obtained are known as the real numbers, and one uses a symbol with a capital R, boldface. A useful visualization of the real numbers is given by the number line, which has long been used to represent the rational numbers. Concretely, just think of a ruler. While the rational numbers, even though to our eyes appear to fill the line, leave a huge number of gaps, such as square root of 2 or b to the power 1 over n in most cases, and so on. The completeness axiom ensures that the real numbers fill the number line completely without any gaps whatsoever. Given the completeness axiom, it is impossible to prove that there indeed exists a real number, c sub 2, whose infinite decimal expansion begins with 0.693147, so that the limit of 2 to the x minus 1 over x is equal to c2. By defining q at the point 0 by this number c sub 2, we have thus extended the function q, initially only defined for x different from 0, in the only way that makes it continuous at 0. So that is, so that q at x goes to q at 0, which is c2, as x approaches 0. A fact that is formalized by the statement that the limit of q at x as x approaches 0 is equal to q at 0. We thus have established a factorization: 2 to the x minus 2 to the 0 is equal to q at x times x minus 0, where the function q is also defined at 0 in such a way that it is continuous there. The points of intersection of the line y equals 1 plus mx with a graph of E2 are the solutions of the equation 2 to the x equals 1 plus m times x. Since 2 to the 0 is equal to 1, we can rewrite the equation as 2 to the x minus 2 to the 0 minus m times x. And the first two differences here is written as q to the x times x. We have this factorization minus m times x and we can factor out the common factor x to get q to the x minus m times x equals 0. As in the algebraic case, we want to determine the slope m so that the solution x equals 0 has multiplicity greater than 1. Clearly, this will be the case if the factor q at x minus m also has a 0 at x equals 0. And this will occur precisely if we choose the slope m to be equal to this number q at 0, which we had determined as c sub 2. And of course, we call this value q at 0 equals c2, the derivative of e sub 2 at the point 0, in complete analogy to the algebraic case. Geometrically, the derivative gives a slope of the tangent line, something that is visualized by the following picture. As we see, here is a point 0, 1, and here's another point on the graph, and we draw the line through these 2 points. The slope of this line is the vertical rise 2 to the x minus 1 divided by x, so it is a factor q of x. And as the point x goes to 0, that is, this point here slides along the curve to approach the point 0, 1, the line slowly rotates and in the end will be a tangent line which touches a graph of the exponential function in a double point. Therefore, this line is now the tangent to the graph. And of course, its slope m is precisely the limit of q of x as x goes to 0, which is this value c sub 2. Once one has introduced the real numbers r, and one wants to use them just like the simple irrational numbers, one must of course extend the domain of exponential functions to all such numbers in such a way that the functional equation continues to hold. This is a fairly routine process, and no new difficulties arise once one has a good understanding of the concept of limit. What we have just done in case the base b equals 2 can of course be done with an arbitrary base b greater than 0. It follows that the limit of b to the power x minus 1 divided by x is equal to some number c sub b. And furthermore, if we fix an arbitrary point a, e sub b at a on the graph of e sub b, let q sub b be the factor in the critical factorization. In order to determine the limit of q sub b as x approaches a, we set h equals x minus a so that x is equal to a plus h, and x going to a corresponds to h going to 0. As long as h is different from 0, one then obtains that q sub b at a plus h, that is b to the power a plus h, minus b to the power a divided by h, where now we use a functional equation here, so we can write this as b to the a times b to the h minus b to the power a, and we can factor out this common factor b to the power a, and we're left with b to the h minus 1 divided by h multiplied with b to the power a. And it then follows that the limit of q sub b at x as x approaches a is the limit of b to the h minus 1 divided by h as h approaches 0, multiplied with b to the power a. That is, we get the number c sub b multiplied with b to the power a. As before, we define q sub b at a to be equal to this limit, q sub b of x as x approaches a. So that makes the function q sub b now continuous at x to the power a at x equals a, and q sub b is that value for the slope of the line that intersects the graph with multiplicity greater than 1. We have thus proved that the derivative of e sub b at x is equal to e sub b at x multiplied with this constant c sub b, which is the limit of b to the h minus 1 divided by h. So let us summarize what we just proved in a theorem. Given a point A in R and any base greater than 0, then there exists a factorization e sub b at x minus e sub b at a is equal to q at x times x minus a, with the factor q, which depends both on b and on a, is continuous at x equals a. Given the central role of the exponential function, we use the key property stated in the theorem to define the general concept of a differentiable function as follows. Definition. Let f be a function defined in a neighborhood of the point A, then f is differentiable at a if there exists a factorization f at x minus f at a is equal to q at x times x minus a, where the factor q is continuous at x equals a. The value q at a, that is a limit as q of x and as x approaches a, is the derivative of f, and it is denoted by d of f at the point A, or simply also f prime at A. If you're familiar with the standard definition of differentiability, you will easily recognize that this definition is equivalent to the above version. If f is a polynomial or a rational function, then we know that the factor q is of the same type, and we have verified that such functions are continuous, were defined. Hence, these functions are differentiable at every point in their domain, according to the above definition. And the result that we just proved shows that exponential functions are differentiable at every point in R, and that the derivatives satisfy the simple formula derivative of e sub b is equal to a constant c sub b times e sub b. C sub b is just the derivative of this exponential function at the point 0. Note that for b equals 1, one trivially has c1 equals 0, because the exponential function which base b equals 1 is simply the constant 1, so its derivative is 0. But otherwise, the numerical values of the numbers c sub b are quite surprising and intriguing. For example, with the help of a computer, one readily obtains the following numerical approximations. Here are some examples: c sub 3, c sub 4. Look at these decimal numbers. They look very strange and mysterious. And given these examples, it is natural to ask if there is a base b star for which the particular corresponding value c sub b star is equal to 1. And one can show quite easily that the number defined by b star equals 2 to the power 1 divided by c2, that is 2 to the power 1 divided by 0.69314, and so on. And you use a calculator, and you see that this number begins with a decimal expansion given by 2.71828, and so on. And indeed, it has this property that its derivative, the number b star, is equal to 1. This number that we just obtained here is usually denoted by e, and it is also called the base of the natural logarithm. It is one of the fundamental constants, analogous to pi, and it is available on most scientific calculators. The exponential function e equals e sub e, little e, with base small e, is called the natural exponential function, and it has a simplest differentiation formula, namely derivative of the function capital E is equal to capital E, or e to the power x prime is equal to e to the power x. Now, recall the various rules for derivatives that we had verified for algebraic functions in part 2. They turn out to remain valid for the larger class of differentiable functions. And the proofs have exactly the same structure that we used earlier, starting with the appropriate factorizations and manipulating these according to the rules that one wants to prove. And the final step then involves applications of natural properties of continuous functions, such as that products of functions continuous at the point A are also continuous at A, or that compositions of continuous functions are continuous. These properties of continuous functions are really quite obvious at an intuitive level. If a formal definition of continuity is used, such as involving epsilon and delta and so on, one of course needs to fill in formal proofs, but none of these involve any new difficulties. We want to emphasize that the proof of the chain rule for compositions that follow the structure of the proof for polynomials that we discussed earlier is much simpler than the proof found in most textbooks. Furthermore, the definition of differentiability that we just gave in this presentation has been introduced, to the best of my knowledge, by Constantin Karatheodori. For example, in his 1950 text, Funktionentheorie. It has been used in lectures and textbooks in Germany beginning in the 1960s, and only recently it has been used in English language texts. Still, it remains quite unknown, as mainstream standard texts in the US and other countries continue to utilize a standard definition of differentiability based on limits of difference quotients. I strongly believe that Karatheodori's definition should become the standard one. It avoids meaningless expressions such as 0 over 0. It uses the natural notion of continuity, and it extends naturally to functions and maps of several variables. And it allows the simplest proof of the chain rule, both in one and in several variables, as well as of the important inverse functions theorem. This completes our introduction to calculus, starting with elementary algebra and leading up to the general concept of differentiable function, including all the standard rules for derivatives. The deepest result that we have proved is that the verification that exponential functions are differentiable. In fact, it has been this problem that guided us beyond the elementary algebraic case to introduce the central idea of limit, which in particular requires the extension of the familiar rational numbers to the much more complicated real numbers. From here on, one continues more or less along more familiar standard routes. Both the algebraic introduction to tangents and derivatives, as well as Karatheodori's definition of differentiability, are used systematically in my book, What is Calculus? From Simple Algebra to Deep Analysis, World Scientific Publishing in Singapore in 2015. A book that covers in detail the required mathematical foundations suitable for schools is being developed. A summary outline of the program has been published in my 2022 article, Calculus, a New Approach for Schools that Starts with Simple Algebra, which is available at the following website. Should you have any questions or would like to discuss this new approach further, do not hesitate to contact me at my email, range@albany.edu. Thank you again for your interest.